Hello, my name is Ryan Finn, and today I'll be talking about leveraging solvers that we built in class, primarily the artificial compressibility solver and the projection method solver to model expansion and contraction pipe flow. So my goal today is to talk about how I modified the solvers that we generated for the expansion and contractions. I'm going to talk about the model setup that I did in order to do this, and then compare and discuss some of the results. Okay, so here are the geometries that I intended to model. It is 6 total, so 3 for each contraction and expansion. And then the idea was I wanted to be able to dynamically modify what size expansion and contraction I had. And the 3 that I chose were 3/4, a half, and a 1/4 inch, or not inch, a fourth of the original diameter, which is normalized to 1 of the pipes. So as we went down to the 1/4, you have much more of a contraction and much bigger of an expansion. And I actually wanted to pass along a helpful debugging tip that I experienced during this, which was the way that this boundaries were set up was through a function, and all I did was pass it ones to generate these plots. So it was a good way to test whether or not my boundary condition setting was correct. Because anywhere where there was a 0, black would show up, and anywhere where there's a 1, white would show up, which would tell me whether or not I was setting my boundaries appropriately. And this was helpful because I originally actually did it wrong. So some of the parameters that I had for the mesh is the domain has an x of 2 and a y of 1. So I basically doubled what our cavity flow problem was that we did in class. And then I kept a mesh consistent across Y and X. So to do that, I had a 100 by 50, and that kind of just balanced based on trial and error, computation time with spatial convergence. I picked a Reynolds number of 1 for this, or 100 for this, because I didn't want to uh, consistently change Reynolds number throughout the test. I was really more interested in changing geometry. Kept a x direction velocity of 1 and a time step of a thousandth of a second. Okay, so for my boundary conditions, they were a little more complex than the lid-driven cavity flow, but still pretty manageable. So coming in on the x side, I have the velocity of x set equal to u, which is 1 in the x direction, and then the y direction velocity of 0. And then in the geometry areas where there's actual piping, this would be like metal, I set the u and v velocities to 0. And then at the outlet, I gave it uh, the 0 gradient boundary condition, where at this edge, I have the last node equal to the one next to it. And then for pressure, I established a pressure of 0 at the outlet to have a fixed pressure condition, and then everywhere else was a 0 gradient condition. So from the one above, with the exception of where the actual pipes exist, there was 0. Okay, so here are some of my results for the contraction, and then I'm referencing it to a reference that I found where this was modeled in Fluent to kind of compare my results. What we're seeing here is X direction contours. And a couple of things that I'm looking for just from like a gross, is this correct standpoint, is we know that the velocity coming out of the contraction is a function of the diameter here, so for a nominal velocity. So I'm looking kind of like this 1/4 should be 4 times the inlet, which is 1 coming in on the left side, and then at the right, we're leaving at over our max is over 4. So that makes sense because we have a gradient, and that ensures that that's a correct, like at a gross level, correct. And the other things I was looking for is, do we have any particular vortices or something like that developing, and I didn't see a whole lot of that, which is consistent with the reference. But we also have a little more of a gradient on the inlet, which could be boundary condition related. Now my expansion results I thought were a little more interesting. They did match the reference pretty well, but I was able to pick up vortex formation uh, outside of the expansions. I did notice one interesting, that the artificial compressibility vortex for the small arc expansion didn't really pick up the swirling as well as the projection method. I think a lot of that had to do with the projection method was able to be a lot more accurate with a smaller mesh discretizations. And here I have listed my reference for where I got those other plots from comparing this to. And thanks for listening.